Hello and welcome to another day of this faculty development program titled GIS and Remote Sensing. The topic for the very first session of the is hyperspectral remote sensing and its application, presented by Dr. Himanshu Govil, Assistant Professor in the Department of Applied Geology at National Institute of Technology, Raipur. He has completed in PG Diploma in Geoinformatics from Indian Institute of Remote Sensing and ITC Netherlands and PhD from Aligarh Muslim University in the year 2014. He joined NIT Raipur in the year 2015 as an assistant professor after having a brief career as assistant GIS officer with World Wildlife Fund, that is WWF India. Hyperspectral remote sensing for hydrothermal alteration and for mineral exploration, image classification, object-oriented classification, GIS, cartograph are his few areas of expertise. He has published more than 71 research articles, which includes different national and international journals and conferences, chapters of different books, and a book. Moreover, he has also guided many masters and PhD research scholars and successfully completed various projects. So, we extend a warm welcome to you and request you to start the session.
Thank you, Aditi, for the brief introduction about me. And good morning to the participants. Today, we'll be talking about another era of remote sensing, which is actually called as hyperspectral remote sensing. Is the PPT visible to all? I'm not sure.
Yes, sir.
Now is it okay?
So keep it in full screen mode.
It's a full screen mode now.
Okay, so we are not able to see it. Is it visible to you?
Slide panel is visible. Voice anytime.
Sure, sir.
Today we'll be talking about the hyperspectral remote sensing and its application. Till now we have, I think, gone for the multispectral remote sensing, which is a broadband remote sensing. Now we do have another option recently, which comes under the category of a hyperspectral remote sensing. And it's allow us not only to identify the zone, it actually allow us to identify the chemical composition of the object. And this is one of the best portion we have in the case of hyperspectral remote sensing. Let's start with the hyperspectral remote sensing, what it is basically. This is a science of acquiring digital imagery of Earth materials. Now, this word is actually important because we are talking about now the material, and when we are talking about the materials, it means we are also talking about the chemical composition. So this is basically a science where we are acquiring the digital imagery of the Earth's material in a very narrow continuous spectral bands, and that is one of the best thing it has. We do have the multiple, in terms of hundreds or thousands, continuous spectral bands rather than spatial. We are actually also talking about the spectral resolution of the imagery. It is also referred as imaging spectroscopy, since it is basically the part of the spectrum in the spectroradiometer. So it is also called as imaging spectrometry. When we're talking about the imaging spectroscopy, we do have some other definition in terms of the composition. It says that imaging spectroscopy for remote sensing involves the acquisition of image data in many contiguous spectral bands with an ultimate goal of producing laboratory quality reflectance spectra of each pixel. It means whatever is available in the pixel, we are getting the reflectance spectra or reflectance spectra means we are actually getting the reflectance of the chemical composition of the material. So when we are getting the reflectance spectra, it means we are getting the chemical composition of each pixel. So we can identify the material in each pixel using the hyperspectral remote sensing. This is what we are talking about, the spectra. It is basically the spectral curve which we are receiving for the each pixel of the image and for all the materials which is actually available in the imagery. This is the basic difference between the multi as well as the hyperspectral remote sensing. When we are talking about the multi, it means we are talking about the many spectral bands, but that is restricted because it has these gaps. These are basically the gap in terms of the spectral range. For instance, we are talking about in general, when we are talking about the multispectral remote sensing in the visible portion, it is generally zero point 0.4 to 2.5 micrometer. So when we are talking about the 0.4 to 2.5 micrometer, we do get multiple bands within the range, but these bands are actually strict with some particular range and it has a gap. So this is basically the gap which we do have in the multispectral remote sensing. In the case of hyperspectral remote sensing, it is basically the numbers which is actually in a huge and continuous. So if you see, these bands are actually giving us a continuous information. It means 0.4 to 2.5. We are getting the bands in all the electromagnetic range between 0.4 to 2.5 micrometer. So by using this, we can actually understand the multiple parameters of the atmosphere. It is, since it is based on reflection, so we'll be receiving the multiple parameters of the chemical composition or the materials which is available on the Earth's surface or the atmospheric parameters. This is one of the concepts which I would like to share, that the range which we are actually covering in the multispectral as well as in the panchromatic region is the same, but the bands which is being covered by the pan or the multispectral are actually restricted. So these are the range which we receive in the multispectral, and in the same range we used to receive in the CARTO sets data or the panchromatic data. So, but this is a range which is actually 0.4 to 2.5 nanometer, a complete range. So if you will see, we are getting a bundle of bands. It is maybe 100, it may be thousands. It depends on the fraction of the visible regions. For instance, 400 to 25 nanometer, we can get a band with a fraction of 20 nanometer, with a fraction of 10 nanometer, with a fraction of 5 nanometer, because the spectroradiometer which is available with us can give us the spectral curve, particularly in the range of 2 nanometer. So when we can receive this in a 2 nanometer, we can get it easily on the Earth's surface as well as from the space-based spectrum. So space-based spectroradiometer or imaging spectroscopy concern is that we can get the same curve or the same chemical composition understanding which we are actually receiving from the spectroradiometer available in the labs. This is basically the curve, or I should say the reflectance. If you will see, this is a reflectance. So whatever you are receiving or whatever the work you are doing on the multispectral remote sensing is basically based on the reflectance rather than radiance. So this is how changes which you are receiving in the multispectral and in the hyperspectral. For instance, this is a Landsat and this is a spectra of the alunite mineral. In the alunite, when we are getting this through Landsat, we do receive only 6 channels, which is actually covering the 0.4 to 2.5 micrometer. In this, we do not get anything in between these channels because this is a vacant portion. So we are not receiving anything. Apart from this, if you are coming to the MODIS, we are receiving one more band here and one more band here. But again, it will not giving you the actual curve which is available in the 1.4 and 1.9 micrometer. These are the two curves which is important. And apart from this, alunite is also having a spectral curve, a spectral absorption feature somewhere in the 2.2 to 2.3. So this is the diagnostic feature of a mineral to identify in the lab as well as in the field. But these features are completely missing in this region. So this is the benefit of the hyperspectral remote sensing, that we can get the particular absorption region of any type of material which is available. In case of geology, it is any kind of mineral mapping. Earlier in the geology, we were talking about the lithological mapping. Now the era has changed, and after the advent of the hyperspectral remote sensing, we are able to get the minerals, particularly altered, weathered and clay, using this technology. These are the details of the sensors which is actually available, and they are actually more on airborne sensors. So these airborne sensors are actually available, but this is not in India except the HIMAP. So these are the airborne sensors. These are the spaceborne sensors, but out of these all, it is only Hyperion and Spree. Spree is also not available. Hyperion is actually freely available in the domain. Rest is basically either from this Mars mission, Chandrayaan mission or something. But the best part of this is freely available on-demand sensor. It was actually, and it has a 10 nanometer spectral resolution and 30 nanometer spatial resolution. 30 meters, sorry. 30 meter spatial resolution. And it was, when it was available, it was an on-demand sensor. So you can provide your place, they will acquire the data and they will provide to you. Out of which for India, it is only the Hyperion data sets which is available. Hyperion is basically EO1 satellites. It is called as the Earth Observing One Satellite Program, which was actually launched by the NASA in the New Millennium Program. It is NNP in the November 2000. So it was launched somewhere in the 2000. It was the first space mission for the hyperspectral remote sensing, and it was developed to demonstrate new technologies and strategies for improved Earth observation. These are the mixture of 3 satellites. One is called as the Advanced Land Imager, ALI. The another one is Hyperion, and The third one is LISA, the Linear Italian Imaging Spectral Array. These are all multispectral except the Hyperion. When we are going to see the Hyperion sensor specific details, it actually covers a spectral range of 0.4 to 2.5 micrometer, out of which it has 35 bands in only the visible portion. It means 0.4 to 0.7, they are having 35 bands. In the near infrared regions, again they are having the 35 bands, and in the short wave infrared region, it means we are talking about the region between 2 to 2.5 micrometer, and it was containing the 172 bands. The spatial resolution of this satellite was 30 meter, and the swath is very narrow. These hyperspectral sensors does not cover a very big broad swath, because the mandate for the hyperspectral data is to reveal the chemical composition, not revealing the ground, which is actually the mandate of multispectral remote sensing. So it covers only the 7.5 kilometer bands, and it is a continuous spectral coverage. Means under this region they have bands in all the regions 0.4 to 2.5 micrometer. These were containing 222 unique bands. The spacecraft was actually single, and the temporal resolution, it means it has a temporal resolution, but the resolution of the temporal is actually 200 days. One more thing which I would like to share with you, that hyperspectral sensor, which is particularly when we are talking about the Hyperion, it does not cover the entire Earth. It covers only the some portion of the entire regions, and out of this, I think for India, we'll be getting around 100 or 200 bands, 200 scenes particularly, because it was a first mission which was actually sent for the technological advancement and technological understanding. It was launched in 2003 for a 10 years program. It means, sorry, 2000 to 2010, but it works up to 2015, 5 years extra it works. So it was the first mission which was providing the hyperspectral data and with the quality. So that's why the NASA have sent another program in the future now. We'll be discussing. This is the coverage. Under this coverage, if you will see, the multiple regions are actually being covered, and the chemical composition of vegetation, soil, water, minerals are actually being covered. So this full region is actually covering almost all the aspects of the multiple domains, maybe the water, forestry, agriculture, soil, everything. So you can use this domain for the chemical composition identification of multiple domains. Another mission which is actually available for India recently is the AIRS NG hyperspectral data. AIRS NG is the airborne. It is actually expected to launch somewhere in 2021. So in India, ISRO and NASA jointly doing this project through airborne survey. The best portion for this AIRS NG mission is, sorry, it has a 5 nanometer spectral resolution. In the Hyperion, it was 10 nanometer, and for this, it was 5 nanometer spectral resolution. It is almost covering the same spectral range around 380 to 2510 nanometer. Apart from this, the most important thing about the AIRS NG is we can change its height because it's an airborne mission. So on the basis of height,
spectral data.
Sorry.
मी काय सांगतो मला डेपुटच केलं पाहिजे बाबा.
Is it a question or normal chat?
No, sir. It was a glitch only.
So
You may continue, sir.
when we can change the altitude, we can actually changing the resolution. So lower the altitude, higher the spatial resolution. So that is the possibility we do have in the AIRS NG hyperspectral data, that we can cover or we can actually understand or change the spatial resolution if it is required. So if any area is having a very good coverage or very good chemical composition disturbances and it's need to be mapped, we can actually cover the higher spatial as well as the spectral. Spectral we cannot change because it's a sensor parameter, we cannot change. Spatial only we can change because it is actually related to the height up to some extent. And this AIRS NG mission was having 425 bands. In the Hyperion we are getting around 220 bands, and now in the AIRS NG it was 425. It is almost just double because in the Hyperion we were getting the 10 nanometer difference, and in the AIRS NG we are getting the 5 nanometer differences. This is how basically a hyperspectral data looks like. It has multiple bands. It has an imagery like the visible region, but when we are pointing out it at a particular place, for instance this pixel, it is giving me the chemical composition of that area. So this is basically between for the SWI region, but we can get the full range from visible to shortwave infrared region. This is how the hyperspectral data requires a processing. It is not a simple processing which we can do in a multispectral because the data which is actually being received through the hyperspectral sensor is actually in a radiance rather than the reflectance. So the radiance data need to be converted into the reflectance data. So that is the one of the most challenging tasks we do have in the case of hyperspectral remote sensing. So to converting the radiance to reflectance and the other processing, we do have a proper chart which is actually starting from the basic pre-processing of the hyperspectral data cubes, then atmospheric correction, then data dimensionality reduction, which is called as the MNF, then identifying the pure spectra, which is called as the PPI, and spectral analysis and classification. When we are talking about the pre-processing, we have multiple type of pre-processing requirement which we need to understand. The first thing and the foremost thing to understand is to signal to noise. Signal is basically something which is actually allowing our spectra to get the better resolution. So it is a signal to noise ratio. Then we have to talk about the band selection because we do have a multiple bands and we do have the atmospheric windows in this region. So in a general, we have to understand what are the bands which we have to cover and what are the bands which we have to remove. For instance, 0.4 to 0.9, 0.4 and 0.9, which is actually the region of OH and HOH absorption. So in this region, you won't get a proper image. So either you have to discard these images or you will have to take the precautions once you are going for the atmospheric correction. Then bad pixel removal. It means if any of the pixel in the image is having the bad, it means the negative values, which is actually having no data, that you will have to remove, because the atmospheric correction, under the atmospheric correction, you will have to understand that no such type of data should enter, because it will change the entire condition of the atmospheric situation. Then the VNIR and SWIR alignment. In a hyperspectral sensor, we do get two spectrum or two spectroradiometer in general. One is basically for the VNIR region, another is for the SWIR region. So these are the two images, these spectroradiometer is actually acquiring the images, and which is actually merged at the later stages and then given to the users. So the alignment of these regions particularly need to be understood. Smiling is one of the error which is actually based on the sensor parameters. So if there is a problem in the sensors, we can understand by using the smiling error. Then the next and the most important is the atmospheric correction. The reflected solar radiation from the Earth's surface in its way before read by the satellite has a transverse through the intermediate atmosphere. When it is coming, the light coming from the sun touching to the surface, and the reflection which is actually sent to the sensor, actually two times it covers the atmosphere. So when it is transferred through the intermediate atmosphere, it contains both the Earth's surface as well as the atmosphere. Apart from this, it is also containing the attenuations which is actually given by the material of the Earth's surface. In order to retrieve only the surface reflectance and study the reflectance properties, the atmospheric components have to be removed, and this process is called as the atmospheric correction. Again, I am repeating because this is a small critical situation. When it is transferring through the intermediate atmosphere, it contains both information for the Earth's surface as well as for the atmosphere. This is basically the information which we does not require for understanding the parameters or the composition of the object, Earth's surface object. So this parameter I need to remove, and the process is again called as the atmospheric correction. This is done by a particular kind of environment which is called as the flash, and the full name is called as the fast line of sight atmospheric analysis of spectral hypercubes, which was actually a developed algorithm or the code developed by the Air Force Research Laboratory. Flash is the first principal atmospheric correction tools that corrects the wavelength in the visible through near infrared and short infrared region up to 3 micrometers. It means up to 3 micrometer we can correct it through the flash algorithm. This algorithm is available in the NV software under the hyperspectral atmospheric corrections. So we can use the NV software for the flash correction parameters. It is also possible that we can use any of the programming language in general Fortran, because the flash was actually written in the Fortran. So we can also use the Fortran language. This is the GUI, graphical user interface of the flash correction window available in the NV software. This window requires multiple parameters. It is not a single parameter entrance, because if you will see it properly, these are the scenes parameters and these are the locations which we have shared in terms of the information. First, it requires the center location, then type of the sensor, then altitude, ground elevation, pixel size, flight date, time. Now, for removing the atmospheric parameters, it requires the model. It's called as the atmospheric model here. So you will have to understand the zone, and on the basis of that zone, you will have to talk about the atmospheric model. Then water retrieval. If the image is actually in that region, we have to talk about the water retrieval. Then the water absorption features, the bands which you will have to provide. Like this, we have to provide all these parameters on the basis of the scene which is actually available with you. So on the basis of these, we can provide the information to the software. And if you will see properly, the input image is basically the radiance. Can you mute the person who is actually giving this noise? Am I audible?
Yes, yes,
Can you mute the person which is actually
yes,
making
yes. I'm going to do that thing.
So
Is
the
it okay?
sorry,
Is it okay now?
yeah, please, thank you so much.
Thank you, sir.
So this is basically the radiance image which you are giving to the system, and the output is in the form of the reflectance file. I'll show you how the radiance and reflectance is actually changing. See, this is the radiance spectrum of the uncorrected hyperspectral image. And once it is corrected, see how the changes you are receiving in the case of reflectance. As I told you, this 1.4 and 1.9 is basically the reason for the OH and HOH absorption feature. So you can consider this or you can remove this. That is up to the user. So this is basically what we have given as an input, and this is what we are receiving as an output after the atmospheric correction. Once the atmospheric correction is completed, we will be doing a data dimensionality reduction because it is containing the multiple bands. And all the bands are not having the unique information. It is called as the data redundancy. So we have to go to identify the bands which is containing the maximum information, or we should scratch it from the whole bundle to get the maximum information. In the case of hyperspectral remote sensing, this function is called as the minimum noise fraction. It is basically transform. MNF is used to determine the inherent dimensionality of the image data, to segregate noise in the data, and to reduce the computational requirement for the subsequent processing. This is basically a two-step process, and it is actually segregating the noise from the data and receiving the maximum bands which is containing the information for further processing. In the first step, based on the estimated noise covariance matrix, decorrelates and rescale the noise in the data. This first step result in transformed data in which the noise has unit variance and no band-to-band correlation. So they based on these eigenvalues and eigenvectors, it is giving you a statistical graphs too. In the second step is a standard principal component transformation, the PCA, which we used to do in the multispectral remote sensing. Principal component transformation of the noise whitened data for the purpose of further spectral processing. The inherent dimensionality of the data is determined by examining the associated images. So in general, these are the MNF bands which we are seeing from, this is a band 1, this is band 5, which you are seeing in the images. So on the basis of these curves, it immediately tells that up to here we are getting the bands. So we can get the maximum also. These curves are actually indicating that maximum information is available here. And after that it is being reduced properly. So number of bands are actually on this side as well as the values of the bands. So on this graph, on the basis of this graph and the visual examination of the images, we can understand which bands are actually containing the pure informations. Once this step is completed, this is basically a precursor step for the next step, which is called as the identification of the pure spectra. And in the hyperspectra, it is called as the PPI, Pixel Purity Index. It is basically a process of techniques designed to determine which pixels are the most spectrally unique or pure. It is basically based on the feature space analysis. If you can understand, in the multispectral, we are doing a feature space analysis to identify the pure spectra, but the dimension are restricted. In the PPI, in the multi-dimension, it was 2, 3, 4 bands, but here it is multiple. So PPI is basically a processing technique which is designed to determine which pixel are the most spectrally unique or pure. Due to a large amount of data, PPI is usually performed on MNF data. It means we are restricting the bands. Once we do have the MNF data, we are implying on the MNF data. So we do have a little bit of restriction in terms of the bands. The most spectrally pure pixel occurs when there is a mixing in the end members. So we will get the most spectrally pure pixel where the mixing of the end members is maximum. PPI is computed by continually projecting n-dimensional scatter plots, which is actually the features plot on a random vector. The extreme pixel, the corner pixel, same as the feature space analysis, for each projection are recorded and the total number of hits are stored into an image. So extremely pure pixels was actually being counted in the multiple data sets. What we are talking about? We are talking about the extreme pixels. These are the extreme pixels. These are the feature space analysis which we are receiving. And we do have these are the dimension in terms of the band. So particularly what we are seeing is a 3 dimension, but it is not 3 because if you see the color 1, 2, 3, 4 and 5. So this area is actually the pixels which is mixed in nature. The corner pixels which we are seeing here, these are little bit of pure pixels. And once you will go to the graph of these pixels, it will be looking like this. So it will be giving you the images of the pixels in terms of the spectra. So these spectra is actually the crux of this hyperspectral remote sensing. Once you are getting that spectra, it means you are actually identifying some pure pixels, and that pixels is basically pure pixel means you are identifying the material, whatever it is, When we are talking about the soil, we are talking about the minerals, we are talking about the agriculture sites, it is the purest one. You can use the same spectra. For instance, if it is uni, you can search the same spectra in the whole image. It means if you have the pure spectra, you have classification methods by which you can search the same type of material in the whole image. How? This is a method which is called as the spectral angle mapper. On the multispectral, we have talked about the multiple mapping classification methods, maybe parametric, non-parametric, in terms of the minimum noise fraction, maximum likelihood classifier or something. But that classification is based on the statistical of the pixels. Here, the classification is basically based on the spectral curve matching. So we have to talk about the angles, the material A and the material B, and the angle is basically defined. This is a user dependent. If you are keeping a wider angle, you will be getting the multiple materials. If you are seeing a narrow angle, you will be getting the particular material. This classification is basically a physical based image classification because we are providing the material or the spectra. It uses an n-dimensional angles. It is not uses only one, it is using the multiple dimensions to match image spectra with the reference spectra. That reference spectra is what? Which we have recently found through the PPI. So this reference spectra which we have identified through PPI is actually being matched with the image spectra in multiple dimensions, and the dimension is based on the input. That input is either you are providing the MNF image or you are providing the whole hyperspectral image. That's depend upon the users. Spectral angle mapper calculates the angle between the spectra and treat them as a vectors in a space with dimensionality equal to the number of bands provided by the users. SAM is an automated method for comparing image spectra to individual spectra. It means we are comparing the image spectra to the individual spectra, or that individual spectra is what? Which we have recently given through the MNF, or we can also use the spectral libraries. Spectral libraries is what? Something which is actually available with the NASA, JPL or something. They are the 100% material based libraries. It means, for instance, if we are talking about the alunite or kaolinite, it is a 100% kaolinite. So how the 100% kaolinite is actually visible in the image, that is also possible. So what we do, we can also provide the spectral library spectra. SAM assumes that the data have been reduced to a apparent reflectance. That is important because SAM is basically an angle-based classification. It matches with the angles provided by the person. So it is actually assuming that the data has been reduced into an apparent reflectance. This is how we used to get a mineral map. If you will see, this is a mineral map and the material is being written here. This is actually a chloride map. goethite map, elite map, any minerals you can, because I am a geologist, I am actually focusing on the minerals. So all the altered, weathered or clay minerals are actually being mapped in the imagery of the hyperspectral remote sensing. Up to here, it is basically all about the hyperspectral remote sensing, its process. Now we'll talk about the application where we can use these hyperspectral remote sensing, and we will also talk about a geological case study which is located in the Himalayas using this technology. Up to here, if any question is there, we can also ask about the questions. Am I audible?
Yes, sir, you are audible. We have Mona ma'am. Yes, ma'am.
Yeah, sir, for the angle mapper which you mentioned in the previous slides, sir, how does one for the hyperspectral? I'm not much aware of this concept, but no, how does one decide upon the angle for the particular material, or it is recommended to first go by the library?
No, angle is basically the user dependent. So it is the user who will have to understand what is the angle. So on the basis of the classification or the spectra, you will have to decide this. It cannot be decided by the system as well. In the in the multispectral, it is a multispectral. We can go for a unsupervised classification. It is not like that. Angle, you must have some known points. In the case of minerals or the materials, you must have some known points, and in that known points reference, you can decide the angles.
Right. Okay. Yeah.
So we are moving to the next one, is how the application of hyperspectral remote sensing is used in the multiple sections. One is in the geology. We are actually identifying the minerals and the types of soils, mixed one. In the soil case, we are also type of soil and the quality of the soil. That is also can be managed by the hyperspectral remote sensing. In the case of snow, we can quantify the cover fraction, grain size, and the melting. In the forestry, we can also identify the type of the forest. Even we can also identify if any disease in the forest type, we can identify by using this. In the ecology, we can also identify the chlorophyll content, the leaf water content, cellulose, pigments, and lignin, because it is all based on the chemical composition. In the coastal water, we can also identify the chlorophyll. We can identify the phytoplanktons, dissolved organic materials, suspended sediments. In the case of agriculture, we can identify the crop type identification, crop disease identification. In the case of urban, we can talk about the materials. It means like you have a civil engineering department. By using the hyperspectral remote sensing, we can identify the construction material which is being used in any of the sites by using the hyperspectral remote sensing, because the material which is being used is actually comes in a general under the visible to shortwave infrared reasons, whether it is a cement or it is a concrete or sand something. So that is we can identify using the hyperspectral. This also depends upon the attenuations. That is important, because for an area which is densely populated, we do get the attenuations. So that removal of that attenuation is most important, because we are actually moving from radiance to reflectance. This is one of the geological study I'm sharing. because in general it is told that this hyper or any kind of remote sensing serves only a preliminary analysis for any of the study. But in this portion, we have actually used these technology in terms of the hyperspectral remote sensing from top to bottom approach in terms of the identification as well as lab analysis as well as the field analysis. These are the integrated program which we have used before going to the field and after the field. And we have found and correlated the multiple results with this technology. So this is basically our study area. If you see, this is the ASCOT area. ASCOT is the border, Indo-Nepal border. If you will see it properly, that this is the Indo-Nepal border. ASCOT is basically known for the base metal mineralization. Apart from the base metal mineralization, it is basically also a place where we can get the altered, weathered and clay minerals pockets. So multiple type of mineralization was available because the Himalaya Varuzani, we do have multiple signatures of metals on the surface and below the surface. When we are talking about the geology, it is basically the Ascot crystallines, the Berinac formations, the Kanalichina formation and the Pythora. In terms of mineral, it is basically the limestones, dolomites and slates. We have divided this whole study into the three phases. One is the pre-field phase, one is the field phase, and the last one is the post-field phase. Pre-field phase analysis means we are actually analyzing the whole imagery in the lab, and we are actually identifying the places where we need to visit. Second is the field work, when we are going to the field to identify the places. Pre-field analysis is important in the case of Himalayas because in the Himalayas we cannot move with a vehicle only. We do have too much of undulating terrain and we have to have a proper name or place where we have to visit. So this is basically a preparation for the field work by the remote sensing analysis, and how the post-field analysis is actually satisfying the results of our field analysis as well as the pre-field analysis. That is also the part of this one. This is one of the most important thing which we have done is the regolith mapping. When we are going to the field, we must have some good idea about the areas or the objects which we need to cover. So for that, we have gone for the regolith mapping using object-based classification. In the object-based classification, we do not consider a pixel. We convert them into an object. So once it is converted into an object, we can understand the areas properly and we can identify the areas. The images which we have used is basically the Hyperion. It was actually an on-demand scene which we have received from the NASA for this study. And we have multiple parameters which we have used particularly for object-based classification. So this is basically the area which we have classified and we have identified before going to the field. We have identified some places which is actually under the regoliths or particularly by using the object-based classification. Once we have identified this one, we have again gone for all this process and we have to identify the pure spectra. It means before going to the field, we can identify the pure spectra and then using the same spectra, we can also go for the classification. So this is how we have identified the spectra from the images itself before going to the field, which is actually allow us to understand what are the mineralogy which is actually available. So those who are the geologists, they can understand these are all altered, weathered and clay minerals which actually being expected with correlation with the geology of that area. Once we do have the spectra, we have classified these images on the basis of the spectra which we have covered, received from the PPI or by own understanding of the areas. Once you have the maps, it means you can have the places where you need to visit. Now the next segment start, which is actually the field work. When we are going to the field, we are actually considering the sites. See, this is one of the site which is actually in the ASCO. Once we are going to the fields, we are getting the multiple clay pockets, gosans, as well as the field signature of the base metals like malachite and azurite. We are also receiving the foldings at the megascopic level as well as in the core zones which we have received. So we do have the signatures that the area is actually being hampered by the tectonic activities, and due to which we are receiving these hydrothermal fluids. In the another website, if you will see it properly, this is the reservoir area, and surface, if you will see the surface, it is fully weathered surface we are receiving. Under this weathered surface, we have identified the gossanized outcrop. Once we have broken this ice crop, we have identified the signatures of the metal content. This is basically the base metals, copper, lead and zinc. This is the surface, how it looks like. These are the which we are seeing here, this and this. These are the metals which we are receiving. Once this is basically how this is the base rock and how the alteration has changed. It's penetrated to these levels. These are the pockets of clay which we have found all around the zones, because the metal mineralization in this area is in a pockets. So outer peripheries is basically known for the alteration mineralogy or the clay pockets. Inner zone is basically the altered one. So we have identified this one. After this, we do have the multiple signatures of the limestone in this area. In another area, we have identified again the hydrothermal magnetites mineralization. If you see it properly, this is all hydrothermal magnetites, which is actually in a schist rocks. Though if you will see, this is not a schist, this is basically an unfurrowed rock. So the hydrothermal magnetite is available in the whole rock. Also here, if you will see, we are getting the hydrothermal magnetites intruded in the country rock. Here we do have the local effects. So these are the veins which we are receiving here. These are the hydrothermal quartz all along the veins too. So we are also receiving this hydrothermal quartz, and all along this hydrothermal quartz we are receiving the magnetites. This is same, we are receiving it here too. This is one of the another zone which we have identified how the alterations are actually being seen. This is basically the talc mines which we have seen in that area, though it was workable, but before going to the field we were not having any idea about this mines. This was only found through the spectral signatures that we do have something in that area. This is the whole zone. This is whole this mountain is basically a talc mountain. Now, once we have completed the field work, we have to analyze the field work in the labs. So we do have the post-field analysis. Post-field analysis means whatever the samples are actually being covered through different sites, we have to analyze it in a conventional geological methods. Apart from the conventional geological methods, we are also defining them in terms of the spectral signatures. One spectral signatures which we have received from the imagery, another signature from the imaging spectroradiometer, which is actually available in the labs. So in the first phase, we have gone for the spectral analysis. See all the multiple sites, we are getting this. This is the lab-based minerals. The signature which you are receiving is a lab-based minerals. Under the lab-based mineral, if you again see that OH and HOH is visible because it was taken through a contact probe. And under the contact probe, we do not allow the atmosphere to be the part of this one. So you can get easily the absorption feature under this range. And if you see properly, this is the iron which we are guessing. This curve is basically meant for the iron, and this curve is basically meant for the ALOH. So this is a light mineral which we have found at almost all the sites. This is the goethite. How the goethite is actually identified by using this curves. So once you have identified this curve, you can identify the goethite mineral. This is basically the iron curve. We can identify this goethite mineral at multiple places. Apart from the goethite, these are the two different spectrum because the goethite is identified in visible to shortwave infrared region, and in the SWIR region we will be getting the another mineral. So that also you have to understand that whatever the material you are trying to identify, which region is actually getting the particular diagnostic absorption feature of that material. That should be known to us. That is possible either by using the spectral libraries available with us or the lab-based spectroradiometers. So once you have the spectroradiometer, you can identify which diagnostic absorption feature is actually responsible for which mineral. This is how the muscovite we have identified. These ALOH absorption features are actually available in that area, and this is actually allowing us to identify as a muscovite. This is a chloride basically. So we do have the multiple absorption features of AL as well as the MgOH. So these are all the diagnostic absorption feature of these minerals, and these are the diagnostic reasons. Particularly this is falling under this reason. This is starting from the 2255. This is one, and another the sharp deep curve will come under 15 to 45. So this is a MgOH absorption feature. So by which we can identify. We do have multiple literature which is available in the same area, which actually allow you to identify which material has which absorption feature. This is how the calcites and dolomites are being identified. These are the all carbonates feature, which is somewhere in the 2335 and 2315. So carbonates can also be identified using this region. So this 2 to 2.5 region is basically having a very importance because we do have all the altered minerals, weathered minerals absorption feature under in the same area. This is basically how the kaolinite and smectite looks in terms of a joint operation. And these are the other minerals apart from the hyperspectral remote sensing we have identified through the spectroradiometer. So we have identified the tals, epidote, talc and chlorides. So this way also we have identified the multiple minerals. This is how we are actually trying to show you the mineral map validation. In terms of the accuracy assessment in the multispectral, we do have the different criteria in terms of the kappa coefficient, user accuracy, producer accuracy. That is basically the statistical parameters. In the case of hyperspectral remote sensing, when we are preparing a mineral map, it is basically the mineral which is actually allowing us to understand or judge the classification accuracy. It is not a statistical accuracy, it is basically a mineral based identification. So if you will see that at all the places we are receiving the clinochlore, goethite at multiple sites. These are the signatures. These are all lab based signatures. These are the classified image of our SAM, spectral angle mapper, and these are the these lab based imaging spectroradiometers using. These are the elite minerals at multiple places. These are the muscovite minerals which we are receiving at multiple places. Now we are moving to the petrographic analysis. Actually, whatever you have received through the hyperspectral remote sensing is basically the spectral curve, and the same curve you have also received using the spectroradiometer in the lab also. But these are all the spectral curves. So to clarify with the conventional geological methods, we have to go for the petrographic analysis. So we have also done a petrographic analysis of all these minerals at sites, multiple sites. So these are basically, if you see, these are the quartz minerals, these are the chlorides, these are the name of the sites which was actually we have identified in the earlier phases. And we do have the signatures of the alteration. If you will see it properly, we do have multiple sites and the signatures of the alteration. These are the talc minerals which we have identified in the muscovite. At the microscopic level also we are identifying these are the folding kind of things. These are the biotite minerals, margarites, epidote, hornblands, goethite at multiple sites, clay products at multiple sites, dolomites. So this is how we are actually verifying our results of the spectroradiometer. Once we have identified the result of the spectroradiometer, we are now going to the another possibility to go for the metal mineralization identification. Because I told you we have identified the base metals in two of the sites. So we have also gone for the ore microscopy. This is how you can see the galena sphalerite is actually in the ore microscopy. So it is basically the validation of the results which we have identified. One more thing which I would like to point out here is that the metal content in terms of the geological parameters, you cannot identify the metal content using the hyperspectral remote sensing, particularly in the visible to shortwave infrared portion. It means 0.4 to 2.5. You cannot identify the metal mineralization or metallic mineralization. What you can find is the minerals which is all along the metal mineralization, maybe maybe in terms of the weathering or something. But metal you cannot identify in this range. If you need to identify the metals, you will have to go for the thermal range spectroradiometer. So thermal range spectroradiometer is one of the option where you can actually identify the metal content available in the rocks. And 2022 NASA is also launching one hyperspectral sensor for thermal region also. In the visible region, one more satellite is expected, which is actually the Everest, which is somewhere in 2021. And in 2022, NASA is also expecting one more satellite, which is based on the thermal region, but in a hyperspectral mode. So it means this is basically meant for the metal particularly. So you will getting the hyperspectral particularly in the thermal region of the electromagnetic spectrum. So whenever we need to go for metallic mineralization identification, we have to go for the thermal region too. But in the visible regions, we can identify the other minerals which was actually available all along the metal mineralization. This metal mineralization was also confirmed through the X-ray diffraction. We do have the X-ray diffraction of metallic as well as non-metallic mineralization. If you will see, this is a galena, sphalerite and cerussite minerals here, and the another side which we have told it is a magnetite. So we have identified the magnetite all along the other minerals, and this is a Gatta-Bagad area where we have identified the talc. So it is a pure talc. We don't have anything else in that talc. So in the X-ray diffraction also we have identified this one. In the next phase we have gone to the ICP analysis. This is the result of the ICP analysis. If you will see, we have identified the lead, zinc, iron and some percentage of gold and copper. So this is all in ppm. So we have identified this whole two sites. One is in a Gosa and in the Kota Razwar area. And these two sites we have identified a very good results. But this area was 1.5 kilometers away from the road. So, and that was a very tedious terrain. We took around 1 day to reach to that place, this area. But we were actually able to locate this because we were actually getting the alteration mineralogy which is supporting to these type of mineralization in that area. So by which we were actually able to identify the different mineralized zones in the tedious terrain of the Himalayas. Some of the publication, if you want, the same study which I have shown you is actually available in the Ore Geology Review. Some portion of this study is in the Ore Geology Review, some is in a Science Direct Elsevier's programs. So these are the all publication. We do have a book. You can also go for this. Same things you will be getting in this book. Apart from this, recently we are working on the Everest NG data. So if you need to know more about the Everest NG data, you can consult these minerals. We are still working on the hyperspectral remote sensing for metallic mineralization. And we have again identified the base metals in the Rajasthan. Earlier study was in the Himalayas, but now the second study would be in Rajasthan, and some portion of the study was published. So at some level you can identify, because here the time was limited, so we have only shown you the result of the hyperspectral study, but still Everest NG have a lot of potential to do some multiple works. So you can also consult these papers. These all are containing the Everest NG's details. These are the some of the publication which is in the conference, Scopus conferences. So the same you can also go for the conferences to study these. Thank you very much. This is all from my side. I'll be very happy if you have any question related to the subject.
Thank you so much, sir, for the presentation. If you have any question, we can ask this question directly to sir. Is there someone who wants to ask something? Yes, Suyog Gupta.